Okay, well I have the AVR Studio tool already opened up here on my screen. So we're here at the welcome page and I can just select a new example project right here, or if I didn't have the welcome screen open I can go to the file menu and go to new example project. That brings up the new example project list. Now there are literally hundreds of example projects in Studio 5, so the best way to find the ones that I'm interested in is to click on Technology here in the left panel, and that sorts all of the examples by their technology area, and right here we find sensors. There are 10 projects in this version to choose from, and I'm opening that up to now see inertial sensor demonstration. Now notice that there are multiple entries of this for the different UC3 boards. Now as we know we're using UC3A3 here, so I'm going to click on that one and then say OK. Now the sensor software in the Studio framework is covered by a license agreement. So that window pops up. I've already read this, so I'm just going to click I accept and say finish. And now it's actually loading the application into my tool environment. And it assigns it a default name of Inertial Demo 1. That's just fine. And now we can see that the main.c file, the prime file in the application, has appeared in our left window. And we have this little file browser in the right window, which shows all of the files that have been included as part of the application, including the various modules from the AVR software framework. So now let's take a look at the in the main.c program and highlight some of the interfaces that are used to support sensors within a Studio Framework application. If we scroll down here to the top of the main function, you can see there are 3 data structures that are called sensor T's. These are the sensor descriptors, and they get initialized at the beginning of your application, and then from then on they are used to identify which sensor your function calls are going to reference for the rest of the execution time. Right underneath that, 4 examples of what are called sensor data T structures, and these are used to contain the data that are actually being returned from the sensors. And there you can see there's one each for the accelerometer, the compass, the gyro, and there's a 4th one for temperature data. In this example, we're actually going to be reading temperature data from the gyroscope. Many of these sensors have temperature as you'll see a secondary feature, and so we're going to be using that as part of the gyroscope. So we actually have 4 types of data being returned, even though we only have 3 sensor devices. We'll scroll down just a little bit. You see the sensor platform init function. This is the primary call to initialize the board as well as establish all of the connections between the sensor board and the microcontroller. And that's used in place of the board init function, which would be more typical in a Atmel software framework application. But you just replace board init with sensor platform init, and that's the only change to the actual initialization at the board level. Then we see 3 calls to sensor attach. These, one by one, initialize the 3 sensors. So you see gyroscope, accelerometer, and compass all being initialized there. Then I'm going to skip down just to the start of our main loop, and this is the endless loop that will be running once the initialization phase is over. And you can see that there's first an LED toggle, so it's going to be blinking an LED each time that we go through that loop. And then there are 3 calls to actually read sensor values, sensor get acceleration, and then sensor get rotation, and sensor get temperature. Those are just getting the values, as you would guess from the names, from the respective devices. You can notice we're using the gyro to get the temperature. Right underneath that you get you see a call to sensor get heading. It's surrounded by this if-else, and we're actually scaled data is true. That just means we want actual engineering units from all these sensors, not just the raw internal values, and that's the setting that you would normally use. So here we use the sensor get heading function, which is going to read from the compass and actually return a magnetic north heading, so in degrees away from magnetic north. It's also possible to read magnetic fields from the same sensor, but in this application we're more interested in a typical real-world case, which is more using a compass for navigation. And then finally underneath that you see a bunch of printf statements, and this is just how the sensor data is going to be sent to the PC host over the USB connection. So that's the quick tour through the file itself. So the next step is actually to build it and get it downloaded and running on the device. So the first step in doing that is to highlight the name of the project. And I can either go to the build menu, or I can take the kind of one-stop method and just go to the debug menu and say start without debugging. And what that'll do is it'll both build the project and go ahead and start downloading it to the device through the JTAG connection. So that's what I'm going to do here. And since this is the first time building this project, this is going to take a minute or so to complete. Okay, so that build is completed, and now a window pops up saying select debug tool. And again, this is only the first time that you run the application, so I need to select that I want to use the JTAG ICE 3 to download to the board, and I click OK, and the download will start. You can see down at the bottom of the window it says it's writing the file, and just that quick it's all done. Now the board here, you can see now has the LED blinking. You'll recall that we looked in the main function and saw that it was supposed to toggle that LED on and off each time through the loop. So that's a good sign that things got downloaded correctly and are running as we expected. But other than that, I don't have a lot to indicate what's going on with these sensor devices. So to see the data that's coming out, I'm going to open up a terminal window. And as I mentioned, I'm using HyperTerminal, but you're free to use whatever terminal emulator is convenient for you. And I'm going to specify the port number that was assigned to this, and I see it here in the list and I recognize it. If you're not sure which port number is the right one to use, you can always go to the Windows Device Manager and look in the port section there. And you'll find one that says AVR CDC device, and that's the one that's been assigned 1000. That's exactly as you'd expect, because the force of gravity downward on the board is essentially a 1000 millig force in the z direction. So all these fields for acceleration are giving us numbers in millig's. So 1000 is exactly what you'd expect. If I turn the board over, then lo and behold, to the USB connection for this board. So I've found the port, I say OK, and then I have to set the baud rate. And the serial output from this application uses a 115/200 as the baud rate. So I find that in the list. The other settings are standard serial output, so I don't need to change anything else, and I just say OK. And now here we have the HyperTerminal window has appeared, and we see the readings coming out. And on the top line we see ACC for acceleration, and then we have 3 numbers, and those are the X, Y, and Z measurements from the accelerometer on here. And below that we see rotation, and below that heading, inclination, and magnetic field strength, and finally temperature. Now if you look at the acceleration, you'll note that if I set it flat on the table, 2 of them are pretty close to 0. For the other values, if I rotate the board, you can see that the numbers change in different axes on that rotation line, because those are the numbers coming out of the gyroscope. The magnetic heading will change as I rotate the board, and that's the readings coming from the compass. And finally we see the temperature, which is pretty steady down there. That's the number coming out of the gyroscope. If I put my finger on here, maybe I can get it to bump up a degree or 2, but that's what's coming out of the device. Now I mentioned the magnetic heading. The one thing to mention is that I have already done a compass calibration on this sensor board and UC3 board combination, and that's important because to get accurate compass readings, you do need to correct for all the local magnetic fields that are present on the board. So there's a separate example application called the compass calibration example, and there's another video here on the Atmel site that you might want to refer to see how to go through that compass calibration, but it's very straightforward, and once those values have been determined, they get stored in non-volatile memory on the processor board, and they'll be there for any future use in applications such as this one. So that about covers how to set up the inertial demo. This is a very simple application, but hopefully it will give you ideas on how to use these interfaces in your application. And sensors are a lot of fun to play with, and I hope you'll enjoy experimenting with them and using the software framework support. Thanks.